Great, thanks very much. Well, good evening, everybody, and welcome tonight to the Brand Community Lecture Series. It's a COVID-safe room, so that's why this is actually a sold-out event, yet it's half full because of the means of the restrictions we have to have at the moment. So a few people might come in as we're going, but you know, that's fine. So I just want to welcome a couple of guests before we start. Certainly to Vice-Chancellor, Professor Eva Leinonen from Murdoch University. Also the Mayor of the City of Kwinana, Carol Adams, is with us here tonight, and also our guest speaker, Professor Jeremy Nicholson from the Australian National Phenome Centre based at Murdoch University. A couple of housekeeping things. If there is some kind of emergency, you'll hear a noise that lets you know that, and just follow my staff out to the car park behind us, the evacuation point, as you can see. But you'll be guided through that should anything happen. If you could switch, of course, your mobiles to silent or even turn them off. And with that, I will hand over straight away to one of our lovely local elders, Ms Teresa Wally, who does many welcomes to country here, and her lovely daughter Rosemary, and hand over to her to welcome us here tonight.
Hi, good evening. I'll just give you a little bit of understanding why we do Welcome to Country. It's just acknowledging we're on ancient grounds, Whadjuk country, but also it's an ancient protocol that's still practiced today to give you a safe stay, safe journey, and keep your well-being at all times while on country.
Kayan, Nijabal Kayan, Murid Yogas and Maman. Welcome, ladies and gentlemen. I know Aboriginal language, but I like to speak English, like everyone can understand me. Rockingham is Wadanji, the ocean, and who meets Mother Earth here at Rockingham at the beach, and when the kids go down to the beach, they usually meet the we meet our apical answers like Maman Wadanji, the ocean that sends us rain and water to feed Mother Earth. And that's how we call it Maman Wadanji. And I am a Whadjuk woman, and my daughters here are Pinjara. And I've lived here most of my married life since I was about 20, when I had my second son in Kwinana at Callista. And I've been here ever since because I don't want to be anywhere else. This is the best place I've ever been. And I was a stolen generation and taken to Nanospray. And there, when I left, I never had a home. But when I got married, we settled in Baldivis. The beautiful people of Baldivis they welcomed us, but we lived in camps until we went to Kwinana, where the men in Kwinana and the ladies and gentlemen in Kwinana said, that should never happen to anybody. We living in the bush in humpies, in camps, and working for the BP. And my husband got a job at the BP. So they all got together, and we had our first house in 1955 or 56, before the referendum. So the people of Rockingham, Kwinana, Baldivis are the best non-Aboriginal people I've ever known. And that's why I'm still here. I've got a lot of friends, and I wouldn't want to be anywhere else. Welcome, everybody. And a little story about our medicine tree, the gum tree. The gum tree is eucalyptus, and you boil a little bit, boil a bit up like this here, and that the eucalyptus oil smell will go right through your house, and if you have it in your children's room, they'll have a good sleep at night. And they'll keep all the germs and the bugs away. Thank you.
Thanks so much, Teresa. My dad worked at BP as well, so maybe they met. Yeah. Isn't that amazing? That's something we all learnt new tonight. Yeah. Thank you, Teresa, and thanks very much to Rosemary for bringing Teresa along. So, again, good evening, everybody. It's my great pleasure to welcome you here to the first lecture in this series, the Brand Community Lecture Series. It is what I hope to be the first of many lectures where we have experts come here to the Murdoch campus in Rockingham to talk about a range of topics of interest to many people in the brand electorate. I want to thank all of you who came here in person tonight. This event is also live streaming and will be recorded and sent around the community later for those who cannot be here this evening. I'd like to thank Murdoch University and in particular Vice-Chancellor Professor Eva Leninen. As many of you know, Murdoch University is named after a great Western Australian academic, Sir Walter Murdoch. Sir Walter was a well-known essayist and broadcaster in the days when more people read more of the daily papers and tune in much more to the radio. He was a supporter of science and of reason, and he recognised education as a means of social empowerment and as a means to improve all aspects of civilisation. As it happens, Sir Walter is my husband's great-grandfather, and we are both really pleased to be working with the university named in his great-grandfather's honour to bring special guests to Rockingham to speak in this community lecture series, which, as I said, I hope will be the first of many. Now, I don't need to explain to those of you listening in tonight or those of you here in the room that the COVID pandemic has been one of the most momentous events in our living history. At last count, more than 33 million cases of the disease have been reported globally. In the past 24 hours, the world passed the grim milestone of 1 million deaths from COVID-19. More than 5,000 people are dying every day. This virus has changed our lives in ways we could never have imagined at the start of the year. People have lost their jobs and many businesses have gone to the wall. The restrictions on our daily lives have been harsh. Families have been separated due to interstate border closures, and the virus has caused the most brutal depression since the Great Depression. So this is a recession we weren't expecting. The economy wasn't looking good, but now COVID really sent us into a place where we didn't expect to be, and which will take a long time for this nation and the world to come out of. As the pandemic rolls on, we're gradually learning more about the long-term health effects of COVID-19, and what we are learning is increasingly worrying. Scientists are reporting that some patients who recover from the acute phase of the disease continue to experience symptoms including fatigue, memory loss, low-grade fever and muscle weakness for several months. Much remains unknown, and on that sobering note, I'm pleased to welcome someone who will shed more light on these unknowns, and that's Professor Jeremy Nicholson of Murdoch University. I'll speak a bit about Jeremy before handing over. Professor Nicholson is an internationally renowned scientist who heads the Australian National Phenome Centre and is also Pro-Vice-Chancellor of Health Sciences at the university. For those non-scientists among us, a phenome is a snapshot of someone's unique biology that results from the interaction between a person's genes and environmental factors such as diet, exercise and exposure to pollutants. And I'm going to leave that to the Professor to explain further. The research emanating from the Australian National Phenome Centre could revolutionise the diagnosis and treatment of the most serious challenge of our times, including COVID-19, but also other challenges such as cancer, obesity, autism and type 2 diabetes. While the Phenome Centre is being led by Murdoch University, it brings together all 5 WA unis, as well as major hospitals and a number of medical research institutes. It is the only facility of its kind in the Southern Hemisphere. Professor Nicholson is a pioneer and a highly cited scholar who has published more than 600 peer-reviewed papers. His lecture tonight, and the first lecture in the community series here in Brand, is entitled Understanding the Immediate and Long-Term Medical Effects of COVID-19. We live in a world in which, bizarrely, there are conspiracy theories about the virus that have been allowed to flourish unabated, and where some politicians and celebrities openly promote harmful treatments for diseases. And the truth is, facts matter. We must listen to the science, and that's what we're going to do here tonight. And that's why I'm fortunate to have Professor Nicholson with us this evening. And with that, I'll hand over to him.
Well, good evening, ladies and gentlemen. It's a great pleasure to be here to kick off this series of community lectures. And as has just been said, COVID-19 has proved to be one of the singular challenges of our time. People like myself, a specialist in systems medicine, systems diseases, spent years looking at possible ways that the world can go wrong and been predicting things like this. But even when it arrived, it's still taken us all by surprise. So the thing about COVID-19 is an absolutely unprecedented disease in terms of its complexity, which I'll explain a little bit more about as we go through, but also because of its unique economic coupling, which has crippled the world. And so have we got that up there yet? You have a very... Oh, there we go. So, so some of you know that I spent most of my life at Imperial College London, and me and a number of my team from Imperial came out only about a year and a half, a little bit over that ago, to build a Phenome Centre here. We built one originally in London. And so in less than a year, we actually managed to exceed the firepower of the Imperial Centre, which I'd spent 20 years building. And it's in a beautiful location right next to the Fiona Stanley Hospital, which is just a short walk away from the main Murdoch campus. And it's situated there to study disease and the origins of disease and the different subtypes of disease. It has in it a huge amount of instrumentation, ways of measuring the chemistry of the body, and I'll explain what I mean by that as we go through, because your chemical signature of your blood or your urine or tissue samples all tell a lot about you. They tell about your genes and your environment that the genes have been exposed through your lives. And they also, when you've got a disease, the different subtypes express themselves in terms of the body chemistry. So we built this laboratory, and it was only opened by Minister Cook in early October last year. And COVID-19 is its first real test, the first thing we actually really opened up on. So what I want to start off on. And you could also ask sort of another question, which is, why here in Western Australia, which has got some of the lightest numbers of cases of this disease in the world, why are we in a position that we can actually do something that is useful and potentially influence what's going on around the world? And I'll explain that as we go through. So, we all want to live a long time. So let's put a background of what Phenomics is, why we set the lab up originally. We want to live a long time. We want to live healthily. We want to live old age. Something called the 100-100 concept, which is 100 years of life and 100 years of healthy life. Now, 100 years of life is not too difficult an ask these days, until possibly COVID-19 came along. But 100 years of healthy life, very difficult. Those last 20, 30 years, really quite tough. And of course, what we want to do is maintain quality of your existence. So in order to understand how to get to that position of the 100-100, we have to understand human biology in much more detail. We have to understand the genetic background of who we are. We need to be able to study the body more precisely to decide if things are going wrong, how to fix them, and when things do go wrong, how to optimally repair that. We call these sort of precision medicine approaches. So that's the aspiration, and it's about gaining knowledge about human biology. So what makes us individuals? What makes us healthy, wealthy, or wise? It's our genes, which we're given by mum and dad when we're born. Actually, before we're born, this all starts to work. Your early development is really important. And then all the different environmental influences, what we eat, how we exercise, what pollutants we're exposed to, how those get into the mix. So most people, if you look at the whole world, the vast majority of people actually die from environmental reasons, not genetic reasons. Something like greater than 95% of the mortality is related to environmental one way or another. But what genes you have does determine how you respond to the environment. And the other thing I've put in there is something called microbiome. That's all the collection of all the microbes that live on your body and in your body, in your gut, on your skin, in your lung. And there is an interface between the world and you. Is actually a layer of microbes, a set of foreign genomes that the environment has to go through. And it's only in the last 15 or 20 years that people have realized that the microbial genomes and the microbes that live with you and in you and on you are just as important in determining disease as your own genes. And in some cases, more important than that. And I'll make a few comments about that as we go through. So, the interaction of genes and environment together creates your disease risk profile for getting anything, right? Your probability of getting a disease is determined by your genes and your environment, how those interact. It also determines the chemistry of the body. So if you can measure the chemistry of the body in exquisite detail, which is what our lab was built to do, you can start saying something about the outcomes of the gene-environment interactions that are personalised to you. And you can extrapolate from that into understanding whole populations of people. So when we built the Phenome Centre, we built it not only for individual health, but we've built it for population health as well, which means being able to scale up the chemistry, to be able to analyse very large numbers, thousands and thousands of people, to understand their disease risks. So, let's just think about the things that kill us. There's quite a lot. It's changed dramatically over the last century or so. And interestingly, the dominant change, of course, is to do with microbes, right, and how we control microbes. So in the late 19th century, sort of sanitation, started to be introduced into London. And then later on, of course, antibiotics were introduced as well. And they were extremely successful at controlling a lot of diseases for a long time. And as a result, people stopped dying of infectious diseases, or a lot of them, and we started to live longer, and then we started to die of diseases of old age, right? So we just were hanging around a bit longer. And of course things like cardiovascular disease, stroke, etc., and cancers get more prevalent in old age, so those became more prevalent as time marched on. But of course there's antibiotic resistance has occurred in the last 20, 30 years especially. And unless that is reversed, we have a very good chance of going back to where we were in the 19th century. So when a new antibiotic has not been introduced for the last 20 years, a new class of antibiotic, they've all been slight refinements on previous ones, and bugs have been around for 2 billion years, 2 billion years of chemistry. They're much better at chemistry than we are, and they can engineer their way around this. So a new drug, if it was introduced now, a completely new antibiotic, would only be about 15 years before the bugs found a way around it. So it's a real big challenge going forward, is that we are not going to be able to control the microbial future of our race. And as we get to larger and larger populations, we're looking at 7.8 billion people on the planet, it becomes more and more crowded. It's much easier to pass on infections. And of course COVID-19 is a special case because it's a viral infection, but we're talking about bacterial infections as well. So that's the background in which we're operating. And if you think about other diseases, so we've got to replace the infectious ones with diseases that are common, that are partly genetic and partly environmental. 2 diabetes is a really good example. This is from some work that was published by Imperial College about 3 years ago now, looking at the way that body mass index, obesity, drives type 2 diabetes. All of these different circles here are all different countries, and what I'm going to do is I'm going to animate it in a moment and show how it changes over about 25 years. The biggest orange circle is China. The next biggest orange circle is India, and the next biggest blue circle is the United States. And what's important here is that over a generation, which is about 25 years. Why will that not go? Ah, there it goes. So this was, there we go. And you can see how, as people get fatter, the diabetes starts to expand, and the area of the circle is proportional to the actual number of people in the country. So China went from being quite small to being absolutely dominant in the world in obesity. That's not a good thing to be, right? But it turns out, fascinatingly, that a lot of this is driven by microbes. A lot of your calorific absorption comes from microbes, and antibiotic exposure, especially in early life, actually helps a development of obesity in teenagers, particularly in boys. So babies that have had antibiotics because they had an infection the first year or two of life are much more likely to be obese as adults. So things that this has only been very recently discovered. So things that we thought were maybe under our own genetic control, right, we now know are partly environmental, partly what food we have, but also partly the bugs that you get even when you're from an early stage of your life. So what does the Phenome Centre do about all this stuff? Why we put it all together? We're interested in large-scale population phenotyping. Let's try to understand the population. We're interested in stratifying patients into different disease types, as I explained earlier. And we do all of that stuff in London. We developed a fantastic centre. I was the head of a very big clinical department there that this centre ran from. But when we came to Murdoch, what you say, why did we come to Murdoch? Apart from the weather and stuff, then there's a much broader range of science was done there, interestingly. So a huge amount of expertise in food science and nutrition, also environment and agriculture. And if you think about it, that's all the things you need in life. You've got good food, you need good environment, right? And that leads towards health. So when we created the Australian National Phenome Centre, we wanted to have this very big picture view with the idea of the understanding human biology and risks in the total environment. And, we set up a lab that's capable of doing that, and with potentially lots of interactions across different groups and, of course, different industries as well. So, if you like, we built this, and it came October, we opened it, and then, just a few months later, we had COVID-19. So I made a decision at the end of January, pretty much, that this was going to be almost certainly the most important disease we've ever seen, and so almost all the resources of the National Phenome Centre, the Australian National Phenome Centre, have gone into COVID research. And it's got beautiful laboratories. These are all mass spectrometers. They're complex machines for measuring chemistry. We've got dozens of these things for measuring all sorts of different chemicals. The idea being the huge range of chemistry we can measure. It's like looking through windows into a house. So if you only can look through the letterbox, you can only see a little bit. But if you can look through the front, the lounge window, the bedroom window, and all these other things, all these different machines give us windows on human biology and human chemistry. So one of the things we've done with COVID-19, and I'll explain the detail in a minute, is to apply all of these things. So we create a panoramic view of the disease that is almost unique in the world. We've probably got more metabolic information in the Phenome Centre about COVID-19 than any other research group in the world. How did we do that with no patients? Well, I will explain that in a moment. But if you go back to thinking about how you deploy these complex technologies, they can be done in two different ways. They can be applied to populations where we're interested in healthy aging and all those other things, and trying to get biochemical signatures that predict what sort of disease you're likely to have, and potentially to inform future healthcare policy about this. But we can apply the same technologies at the patient level, something called clinical phenomics, to look at the different subtypes of disease. So the word phenomics, what is that? I think people know what a genome is. A phenome is just the product of the interactions of genes and environment. It's who you are. So that can be expressed in lots of different ways, physical ways, height, weight, those are phenomic properties. Your blood cholesterol level is a phenomic property, but it's a chemical one. So what we do in the Phenome Centre is measure tens of thousands of chemical properties of your blood or your body using these fancy machines. And from the clinical phenomics, we can develop new diagnostic technologies and potentially new prognostic technologies, which of course would be very important and valuable in diseases like COVID-19. We wouldn't be here today talking if Professor Morrison had not been at the WISH conference in Doha in 2016 when we set up formally the International Phenome Centre Network. That's a group of laboratories with similar sorts of instrumentation working on the world's biggest problems. And basically, we signed the deal, didn't we? And we set up the Phenome Centre. It's just then, at that time, he hadn't persuaded me to come and run it. So he did somehow, but here we are. But it started at a major international conference. The guy on the left there, Lord Darzi, former Minister of Health, the UK, Dame Sally Davis, Chief Medical Officer of the UK. So it's set up at a very high level. And there are now a whole series of these laboratories around the world linked in together. And we have now, for COVID research, we've signed agreements with 12 different laboratories around the world, which is one of the reasons we've managed to get a lot of samples into Australia when the disease is actually comparatively rare. In fact, I think we might have the only COVID-19 import license in the country. When everybody's trying to keep it out, we're shipping it in. But under very careful, controlled circumstances into a biosecurity laboratory. So the aim of this consortium, this network, was to join together to attack the world's greatest diseases. Right? Because these diseases are so big, they affect everybody. No one group, no one university, no one country can tackle them. You need international collaborations. And what more important is there than collaborating together to fight COVID-19? And the idea was ultimately we would develop atlases of biology, human biology, and also of disease and how it expressed itself differentially around the world. So, let's do some basics. So, what is COVID-19? Well, COVID-19 is a disease caused by the coronavirus, beta coronavirus, the SARS-CoV-2 virus. And the CoV-1 was the one that caused SARS, right, which in the early 2000s. People have said it's like influenza, especially people like Donald Trump. It's not at all like influenza in multiple different ways. It's about 4 times as infectious, and influenza is very infectious. And if you look at the overall mortality statistics, and those are now emerging, it's about 40 times as deadly. So it's really pretty serious disease. Incubation, probably it's variable, 2 to 14 days, can be very, very quick. First symptoms to severe disease usually take about 10 days. So at day 10, you either sort of get better or you get very significantly worse. A lot of people, at least 80%, are asymptomatic. We think that might be much higher than that as well. There's this sort of hidden group of people that have been touched by COVID but possibly don't even know that. And that's actually quite worrying, as you will see shortly. The thing is that once you become intubated and you're in critical care, you go up to about a 70% chance of dying. Right? That's more serious than almost any other type of hospital interment. Right? If you get it, so one of the most important things is to actually stop you getting into critical care and stop you getting intubated, because then you've got a reasonable chance of saving your life. Turns out, it's quite interesting, Germany, for instance, has got lower mortality statistics than the UK, right? And it turns out there's a very simple reason. The Germans put people on oxygen about, on average, 3 days earlier than the UK, and it stops them going into the most critical phase. And why didn't the British do it? They're afraid of running out of oxygen. It's really dumb things that kill people in this disease, okay? So afraid of running out of oxygen, so you don't use it up, and then when you do need it, you're going to die anyway. So it's much more complex, as I explained, than a lung disease. It's a multi-system disease. It's genetically, it has origins in a bat and a pangolin. And that's pretty much certain now. I know there's a lot of controversy exactly about that, but that's what it matches from its genomic sequence, and it's of natural origin. No one's smart enough to have engineered something as nasty as this. Humans aren't that smart. And of course, it's one of many emergent zoonotic diseases threats. A zoonotic disease is a disease that originates in animals and then overspills into the human population because the animal is brought close to humans that shouldn't really be with it. So humans don't live with bats, right? And humans don't live with pangolins, and pangolins don't live with bats. But in markets in Wuhan, humans and bats and pangolins come together. And the way that the virus comes about is rather complex. In fact, both the bat and the pangolin had to have a coronavirus at the same time. A bat coronavirus and the pangolin coronavirus. And basically the bat coughs on the pangolin or the other way around, and they swap over a bit of genetic material. So both viruses have to be replicating at the same time in order to create something like this. And my analogy for this is like if you've got a document you want to photocopy and you've got accidentally get another page from another document put in, and you put it in the copier and you press 2 billion, right, copies. That's what happens when you get 2 documents, 2 genomes spliced together. And that's what happened, we think, with the new coronavirus. It's still evolving. There's still point mutations. So in the United States, there's a mutation of a single gene, all right, in the spike protein. I'll come back to the spike protein in a moment. And it just makes it more infectious. Not necessarily more dangerous, but just more infectious. So statistically, it can spread faster. And that can happen a lot with viruses. We know every year we get a new version of influenza vaccine because the virus mutates. Now, we don't know whether that's going to happen with the COV2 virus or not, but there's no reason why it shouldn't happen. So people are in a race to create a vaccine, and yet we don't know how long that is going to be useful for. In fact, there's lots of question marks over vaccines, which we can talk about later on. The actual virus, the coat itself, the so-called spike protein, it's very complicated. On the left-hand side is the protein structure of it, and it's got fats on it and all sorts of stuff like that. It looks a bit like a key, and it's exactly what it is. It inserts into a lock in the cell and turns, and it lets the virus in. It is very much like a lock and key. So, one, the vaccines, a lot of them, they're trying to raise antibodies to the key, so you can stick onto that, except it's not a cell, it's something that will kill the virus or neutralize it. But also you can think about how drugs can bind to that protein as well and stop it getting into the lock. So those are let's call it the therapeutic strategies towards this, but it's very, very complicated. You already mentioned what the death tolls are. This morning's 33.5 million people dead. And in Australia, very few cases, even though we've had that second wave, which is actually about 3 times as big as the original one. But a very light touch in Australia, which you'd feel very, very lucky. And Western Australia in particular, an extremely light touch. We thought we were going to get it like London, and we didn't. I'm tempted to say missed the bullet, but the bullet is still flying. We haven't missed it yet, okay? But the important thing is if you look at the recovered number on the left-hand side versus the dead, it's with over 1 million dead, comes out about 4%, right? So there's still a lot of infected people, but really that's 4% is a very high rate. Influenza is 0.1%, to put it in context. And the other thing is, top right, is the spread, now that we've had large numbers of cases, between men and women. Men are on the left in red and women on the right, and these are different ages. And you can see it's pretty evenly spread. And in fact, you're just as likely to get it when you're 20 as you are when you're 60. It's just you're more likely to die when you're 60, because what this disease works on is a lot of residual disease factors that people build up throughout their lives. You build, as you get older, obviously you age, all sorts of things start to go wrong, and everything you've got, if you wanted to have a simple description of coronavirus, what it does, it makes it worse. Everything you got, this thing turns the volume up on it. And that's one of the reasons why there's lots and lots of different effects of this virus. In the UK, let's just show you, here's Australia, second wave, hopefully close to over. UK starting its major second wave. And of course, we're now going into flu season in the UK. If you get flu and coronavirus at the same time, very, very serious indeed, and that's going to have even higher mortalities. So people need to be getting their influenza vaccines to keep that out. Not that it'll protect you against the coronavirus, but it will stop you getting 2 respiratory viruses at the same time. And there is no reason whatsoever why this should not continue and continue and continue. Because this disease is so infectious, if you miss it, it will get out and it will cause another wave. So we are safe at the moment in Western Australia because the state is locked. So that cannot stay locked forever. So we have to be thinking very carefully about how we unlock it to stay safe. Also, people think they're indestructible, even now, especially young people, and the pandemic is driven by young people spreading it, acting inappropriately. But it's very difficult to actually control these things. And of course, the latest spike in the UK is definitely to do with young people. The other thing is, I notice you're all beautifully socially distanced at about 2 metres. Unfortunately, the distance is 4 metres. So we should only have a quarter of the number of people in this lecture theatre as we have at the moment. So the distance, 1.5 or 2 metres, which is being used, is a guess. It's not based on science. The science says 4 metres, right? But it's a guess that's prudent because, of course, you cannot operate anything properly with 4 metres spacing. You can't operate bars or restaurants or anything. So I think that number was just picked out there saying, well, that'll work. But it doesn't, okay? The testing is poor still. There's a huge amount that goes on about of air is spent on testing, but there's still, for the nose swabs, it's still about a 30% false negative rate. The tests get better and better, more and more sensitive detecting the virus. But if the virus is not up your nose, you won't detect it. And that's the problem because, as we'll see in a moment, there is a sort of narrow band of time when you can test positive. And if you miss that, it doesn't matter what test you're using. So we've been trying to come up with a different type of testing. Vaccines, well, don't use the Russian one, I would say. Russian roulette vaccine, I would say that one is, right? It's got no phase 3 clinical trials. That's when we test for real safety. It's actually, as far as I know, it has got no phase 1 or phase 2 trials, but it's very impressive. It's just been pushed into various people who don't have much choice in it. But the fact that it's called Sputnik 5, it tells you it's a political thing and it's nothing to do with science. In any case, people will die as a result of taking this vaccine if it's applied at scale. And I believe the Chinese have also got a vaccine that they claim they've been testing as well. I don't believe it myself. There's over 140 different vaccines. Actually, it might be as many as higher than that, 170 maybe now, that have been tested out around the world. It takes a long time to do this, years normally. Usually 6, 7, 8 years. But the amount of money that's gone into this is bigger than anything in my experience in any disease. So there is a chance that something will be produced. It won't be on President Trump's timescale, I can absolutely assure you of that. But there will be eventually something. But when, we really don't know. It could be 6 months, it could be a year, it could be never. Right? There was never a vaccine has never been developed for HIV. 30 years of trying, no vaccine, okay? Just doesn't lend itself to it. And this is a complicated disease as well. So we just don't know. We can only hope that there will be a vaccine or some other therapy, probably a repurposed antiviral therapy, that can be applied and used relatively soon. I was told earlier not to make this doom and gloom, right? But it's actually, there's not very many good stories on this. I'm going to tell you the way it is, and I'm going to tell you about our hopes for being able to do something positive. So this paper is entitled Nature's Virtually Perfect Biological Weapon. It wasn't developed as a biological weapon, but it works incredibly well, and it has multiple stages of the pulmonary. Now, most people concentrate on it as a lung disease, but it's much more complicated. And if you look on the right-hand side of this diagram, you'll see that it does a lot of other things. Now, these are not just side effects. These are real effects of the virus. The virus causes these things. It causes multiple micro blood clots, which explains the multi-organ nature of this disease. It causes a lot of GI problems, especially in the early stages of infection. The fecal route of excretion of the virus is very efficient, so fecal samples are very, very loaded with virus. And of course, in countries where there's a lot of diarrheal diseases, like India, etc., that makes that all the more of a problem. Dyserythropoiesis, that is failure to make red blood cells in the liver, and porphyria. Porphyria is a defect of hemoglobin synthesis, and it leads to elevation of toxic chemicals, some of which cause cancers, so there's all sorts of problems potentially there. A high proportion of patients have liver dysfunction. 77% of COVID patients actually have some level of liver dysfunction. A very high proportion, probably 60 to 70%, it depends on the population, also have diabetes, which is not just they have it already, it actually causes diabetes. And there are known rare causes of viral diabetes. Cytomegaloviruses can cause it, for instance. So that is currently under study at the moment, these other manifestations. Renal damage. There's loads of stuff now on different neurological effects. Skin rashes, sores. Children have the so-called COVID toes, where they get little red toes and things like that. Kawasaki disease, that's a disease of the blood vessels. It's a very, very rare genetic disease in children, but this COVID-19 can cause it. And there's also atherosclerosis and heart problems as well. So it's almost, you can't find hardly any organs that aren't affected at one level by this. So that's going on in the background of the respiratory disease. And the doctors are looking at the respiratory disease, and at the moment they're not terribly well focused on the other manifestations, which could be persistent for a very long time. So there's now something called long COVID, nasty name that in British have coined. But at least half of this is about a month or so ago that this was out, but at least 500,000 people have got long-term effects affecting multiple organ systems, including obviously respiratory, but other organs as well. And even more scary, especially when you hear Donald Trump saying, you know, children are virtually immune, it's actually type 1 diabetes can be caused in children. This comes from Imperial College London. Possibly as many as 20% of children who get it. And it's rare in children, but when they get it, 20% can get type 1 diabetes, a lifelong disease. Okay, so we really need to be much more aware of these background problems, because not only does it affect the therapy that you're giving to the patient, because they're complications that can lead to morbidity and mortality, but we need to be worried about the recovered people. What does recovery mean? Is it recovery from the lung, or is it recovery from all of these things? And how do we know when you are indeed recovered? This table shows you about the testing problem. So these are all the different, sorry, it's a bit complicated looking, they're all a bit different timescales of things you can test. If you look at the red bump there, that's when the virus is up your nose and you can get it with a swab. Obviously it goes up quite steeply and comes down quite steeply, so if you test too early you'll miss it, if you test too late you'll miss it. And then the body responds, not everybody responds equivalently, but the body can respond by building antibodies, which will help protect you. And then they have various other curves as well. But there are sort of gaps between the virus detection by the PCR method and the antibody detection. And we're hoping now to create new tests based on metabolism, the things that we measure in the Phenome Centre, so-called phenoconversion tests, which will not only detect earlier, but also detect the gap between the PCR test, which are the swabs, and the antigen tests, and indeed the same technology applied to study the long-term effects of disease and whether or not you have genuinely recovered. So, what are the long-term questions? Right, as we say, do patients ever really fully recover from COVID-19? And if you look at the SARS literature, and also the MERS literature, you find 12, 15 years on that people have still got diseases that they were picked up as part of that process. I'll come back to those in a moment. If you've had the disease, can you be reinfected, or are you immune? That's still an open question. We do not know the answer to that, but the antibody testing indicates that in many people the antibody response goes away quite quickly, maybe 3 months, 6 months, or a year. In which case, of course, the vaccine's not going to work terribly well, because you've got to be able to raise those antibodies and keep them high. Although, quite frankly, it's much more complex than that. It's not just about antibodies, it's also about the so-called cellular immune responses as well, which are also very important and have been less studied so far, although people are starting. When they've recovered, whatever that means, what are their long-term disease risks like? Well, they've potentially had very serious lung damage, which will take potentially months or never recover from that. So other lung diseases become more likely as well as a result of the first encounter with the virus. And then diabetes, metabolic, gastrointestinal and liver diseases, all found long-term with SARS. Okay, 60, 70% of people, right, with hypertriglyceridemias 12 years after SARS and things like that. And we're seeing those in the acute patients, right, COVID-19, so we might expect them to be present long-term as well. There's some really horrible ones, neurological diseases. Unbelievably, Parkinson's disease, there was actually an epidemic of that following the 1918 influenza epidemic, and there is a viral origin theory for Parkinson's disease, and we in our own laboratories have found some evidence that connects the abnormal biochemistry to very high Parkinson's risk, right? And of course that's yet another potential manifestation of the long-term disease. And then, of course, there's the problems about ethnic minorities as well. In the United States and the UK, there's like 2.5 times the death rate in the black community. And we have to worry, of course, about the Aboriginal communities here, who've actually largely been spared from this, very fortunately, but they may have different risk factors for not only developing the disease and the severity of it, but also long-term. And another question is, are we prepared for the next wave? We certainly weren't prepared for this one. We really were not prepared. People talk about preparedness to do with things like availability of PPE, the protection equipment, which there wasn't very much of. But it's actually not that. That's not the level of preparedness we're thinking about. It's the intellectual preparedness for something that we have never experienced before as a race. We have never experienced anything on this scale before, and we haven't seen the last of it yet, unfortunately. But we need to be able to keep hope, and we need to use technology to try and solve the problem. So what's our response? Well, firstly, we've deployed all the staff and all the resources to studying the natural history of disease. A lot of this has been bankrolled by Murdoch University, so thank you very much, right? We've had money from charities, Spinnaker Foundation, McCusker Foundation, things like that. We've had some money from the federal government. We're still trying to get more money out of the state government. That's another story. Let's just park that one. The International Phenome Centre network was activated. We're now collaborating with people, sharing data, even starting to share samples for international harmonisation, and we've also been publishing on this as well. This is our grand model. How are we going to get, it's complicated, I know, but we're trying to study the whole natural history of the disease, from the population, whatever that health state is, into the disease, through the disease, and out the other end. That's the natural history of the disease. And we're also using, for instance, the Busselton study. I think many of you have heard of that. It's a big epidemiological study. It's been going for a couple of decades now or more. And it's basically got a lot of background chemistry about what Australians are like biologically. So if we're assessing whether people have recovered as a population, we need to know what they've got to recover to. So we're using the Busselton study samples to find out what normal Australian biochemistry looks like, and using it as a reference point with which to compare the so-called recovered patients. And then in the middle of this complicated looking diagram, that is what we call the patient journey, from going into the hospital, the interventions, right, and the outcomes. And we're modelling those, and we're using all our chemistry to follow the patients, see when they're getting worse or getting better. We also have a very large number of samples that are coming from the University of Cambridge, right, in the UK, Addenbrooke's Hospital. They probably have more patients than the whole of Australia. And we have one of their sample collections, which has got multiple severity types, and really importantly, a longitudinal study of the development of the disease. Right? That's actually very poorly represented scientifically around the world, and this is probably the single best scientific study in the world of the disease, and they're being analysed in our laboratories here in Western Australia. But it's important also that we try and look at the patients who are recovered or who've been exposed to the virus. We need to know if any of them have become diabetics, if they've got liver damage, because we need to be able to give them therapy and improve their health. We simply do not know what the scale of this is yet, and we can only hope that it's not as bad as the original SARS. In the Cambridge study, all the patients are going to be followed up at 3 months, 6 months, a year, and beyond, and we will be following that story all the way through. Complicated looking slide. I don't want you to dwell on this. These are all, I want to show something about the windows that you use. These are 9 different sets of analytical tools that we're using to light up different parts of the biology and biochemistry of the disease that we're using the Phenome Centre. So we bring this incredibly comprehensive biochemical view of the disease, more comprehensive than anything else in the world. And we coupled with the best samples in the world, we should be able to get some real answers. Interesting thing is, every single one of these things works brilliantly well at detecting the disease. They all do, right? What we're trying to do at the moment is figuring out what the best bang for the buck is if we're going to develop a new test to try and augment the PCR tests and the antibody tests that are being used at the moment. With one of the prime aims is to keep the state safe. So when we unlock, we need to be able to screen people to make sure that when they come in, that they genuinely are negative, not with a 30% chance of us missing it because we've swabbed them at the wrong time. So that is an ongoing problem, that applying all of these methods and analysing the vast amounts of data that come out to find the best way forward. Our first paper came out a few weeks ago, joint with the University of Cambridge, as a matter of fact, and what it revealed from blood plasma is all the horrors that I showed you in one go. Right, the blood plasma tells you all of those stories about the different manifestations of disease, the diabetes, the liver damage, the heart damage, the cardiovascular injury, the renal damage, you name it. And now, the very latest, just this week, actually, we've discovered the smoking gun for Parkinson's disease as well. So that's bad, right? So what do we know? We've developed 6 prototype tests for phenoconversion. We're going to nail that down to 2 within the next month. They're all running at a 95 to 99% sensitivity, which is better than the PCR. The false positives are also very low, and we're looking at tests which are actually relatively cheap to do, right, in terms of the actual cost, the reagent costs, and actually running them in the laboratory. And they can all be done quite quickly. We did a test run, where we got some samples from the critical care in the Fiona Stanley, which is, we're on that campus, and it was only half an hour from the patient into our laboratory, in the machine, and about another 10 minutes to make the diagnosis. So we've got effectively close to real-time diagnostics, so long as it's not scaled up so that we've got thousands of people coming through. If it's a few hundred, right, we can actually cope with that as it is at the moment. The biochemical profile will reveal diabetes, liver dysfunction, porphyria, renal damage, acute systemic inflammation, cardiovascular and atherosclerotic damage, neurological disease, possible links to Parkinson, as I said. And another one which is really like sticking your finger in your eye, right? Just when you thought it couldn't get any worse. Paracetamol, widely used painkiller. People have been taking so much of them because they're in pain that they're actually in paracetamol overdose. Right? And paracetamol is a liver toxin. You've got the disease that causes liver damage, so the last thing you want is paracetamol. Right? So we're working with Cambridge on writing a paper now about contraindication of paracetamol for COVID-19 pain mitigation. This is made doubly worse because in April, a French group wrote a paper saying that ibuprofen seemed to make it worse, and so everybody moved over to paracetamol, right? And in fact, ibuprofen doesn't make it worse. Okay, it was interesting. Remember the shops were all running out of stuff? I went to my local shop. Paracetamol completely run out. Ibuprofen stacked up still. All right, so I knew that this wasn't a problem, so I'd got the ibuprofen. But here's something that's really simple and actionable. Stop them having paracetamol, right? It'll reduce the mortality. So that's a directly actionable piece of information that came out of our laboratory, which will be important around the world. It'll save people's lives. And then recovery. We need to redefine what that means for a systems disease. We can map what recovery of the respiratory is, but maybe not the rest. Just to give you a very simple example, sorry, this is a complicated looking diagram, right? But this shows you the sort of science we do. Very simplified version, right? We've got many, many more samples now. But basically, we can use the chemistry to classify, to map the patients. So the group in green on the left-hand side are normal people, healthy people. They're all quite close together, physiologically similar. The ones in red are people with COVID-19, really a long way apart. The triangles are from Royal Perth and the circles from the Fiona Stanley, but the important thing is they're separated. So we can ask a chemical question, what's the difference between them? Those become the new diagnostic biomarkers that we apply when we're trying to diagnose a disease. And then what you can do is you can test it by putting in people from the COVID clinic who had respiratory symptoms but were tested negative. Those are all the grey ones. And you can see a lot of them map with a control group, so we know that they didn't have COVID. Some of them map with the COVID positives, and that includes me. So I got COVID-19 when on a conference in Italy in February. I was exhausted when I got back, and I thought it was just really bad jet lag. But in fact, I had an atypical version of COVID-19, and I self-isolated because I couldn't get out of bed, right, for nearly 2 weeks. And then this test was done with me. I was originally a control patient, right, control person. I tested smack in the middle of the COVID-19s. We did this antibody test on me, and I was positive. So I'd had the disease and didn't know about it. The other grey ones as well, we subsequently tested with the antibodies, and they'd all been falsely labelled as being negative by the PCR method. So the metabolic test is better than the PCR, and it's as good, certainly as good as the antibody test. And the other thing about me, that was 4 months after I was in Italy. So I still have remnants of the disease, and I can tell you I have diabetes now as a result of it, long term, so I'm now on medication. So thanks a lot for that, okay? But is there an upside to that? Yeah, there is, because I'm a scientist, I'm working on it. I happen to know that I had that, right, which I didn't suspect before. So I'm now can be on therapy. But how many people have had this that didn't know they've had it, and they might be diabetic, might have liver damage, etc.? Okay. Nearly at the end, you'll be delighted to know. So I'm not going to go through this in detail. How can we put our tests together in a way that makes it useful? So trying to keep us safe, protect the borders. The PCR on its own is not good enough. At the moment, somebody comes in, say they come in on a plane, they're put into quarantine, they're tested on the first day of PCR. Depending on exactly when they might have got infected, assuming they are, it's possible that it was either, it could be before the virus has gone to high levels in the nose, so they might have missed it. And then they're tested again about 2 weeks later before they're let out, and then the virus could have gone down again. So it's possible, just if the timing's wrong, to miss somebody who's positive. And when you get enough people coming in, that will start to be a problem, and we'll start to have spikes again. So what we're proposing is you do one of our tests, we haven't decided exactly which one yet, but they all work pretty damn well, together with a PCR. And it's working on a different way. It's not detecting the virus, it's detecting the effect of the virus on your body's biochemistry. And the chances of it missing both is actually very low indeed. And then we test them again at a week, and we test them at 2 weeks. So we increase the frequency, and we also do a blood test. That is a way of making this state safer if we can apply it. Okay, and so we think also of 3 different types of testing in terms of the natural history of disease. The acute test of the sort I've just mentioned, a so-called phenoconversion test based on the fact your biochemistry changes because you get all these other side effects of the disease, but also severity prediction too. Our latest data from Cambridge indicates that we can predict the death of somebody the day they go into hospital, well before they go into critical care, based on their abnormal biochemistry. And if you know early, right, that somebody is going to get very, very sick indeed, then you can start to make interventions. You can give prednisolone, anti-inflammatories. You can potentially use some broad-range antivirals. You can oxygenate them. There are actionable courses that you can take if you know someone's going to get sick. And then the next part, the final part that we're working on is the what we call post-COVID-19 syndrome, which is all of those other things rolled in together to try and assess the population as to how badly they've been affected, and to advise people on what they need to do to be healthy in the future. So there is some light at the end of the tunnel, at least in Australia, right? We've been lightly touched, thank God for that, right? We need to stay safe, and we're trying to develop the technology that will help us do that. So I've finished. Thanks to all the Murdoch team, UWA, Cambridge, etc., and all the other people that have made this possible. And you, for kindly listening, I'll be happy to take any questions.
Well, much, Jeremy. I think there's a few takeaways, but of course the main one is don't get it. That would be a start. We've got time for a couple of questions, if there are any in the audience. I don't think we need to hand the mic around. It's quite a good acoustic. So does anyone have a question? Yes, John?
There's been a lot of international talk about the hydrochloroquine drug. Do you have any information, or can you? Oh, thanks. Do you have any information on that particular drug and side effects if used?
Well, I mean, it's got a lot of well-known side effects. It's a pretty toxic drug, and you don't want to take it if you don't have to. But there is utterly no evidence that it actually is efficacious in any way. There's multiple studies now that have basically said that it's not worth taking, and it's never been recommended. Although it's obviously used for malaria. But it's never been recommended for anything outside malaria. There's no precedent for using it, and I have no real idea where that idea came from, that it would be a good thing. There's now probably dozens of studies now that show that it's not efficacious at all, and in fact it's potentially dangerous because it causes heart problems.
Right. And the other question I want to ask you was about the why aren't we conducting blood tests initially instead of the nasal thing? Why aren't we going straight to the blood?
I have no idea. I wish. Well, I mean, because the blood. Somehow people think it's more invasive, but if you've ever had one of these things stuffed halfway into your brain, you would not want to have it done, right? I suspect that having a blood sample is considerably less painful than having one of these nose swabs. So the thing is that it's the way that people think. You look for the virus. The virus is the thing that causes the problem. It is in your nose for part of the time, and that's what people have historically done. They've swabbed things, but it's not for just the sort of natural history of this particular virus. It doesn't really help you very much. There's still it's easily missed. So we went for something just completely different, what we call an orthogonal way of doing it at 90 degrees, not looking for the virus, but looking for the biochemical effects of the virus. And that's why we did all those different range of tests, because we wanted to find the window that would actually be the optimal way of saying that it's the COVID-19. What I didn't expect, actually, for every damn window to work. I mean, every machine we use actually can show up the virus because it has so many different biochemical effects, like an orchestra of effects.
So would a blood sample be most effective?
I think so at the moment, yeah. I mean, I think we could probably develop a urine test as well, because your biochemistry of your urine is also very distinctive. What is amazing to me is that nobody wanted to actually give us urine samples from the hospital, right? I mean, it's, oh, no, it's horrible urine, right? I mean, if you think about quarantine, you know, that's actually much easier if you're in a hotel, is to leave a pot of piss outside the door, isn't it? They'll have a nurse come in, right? I mean, you know, so we've got a very small number of urines, and it actually looks quite interesting, but we haven't got enough to do anything statistically yet. Yeah,
there are many options. Carol, did you have a question there? Oh, do you want to wait for the mic for a second?
Oh.
Just for the streaming. Sorry.
Hello, look, that was really interesting, Carol Adams from the city of Kwinana. One of the takeaways that I got was the distance of 1.5 and 2 metres could be a guess. It may not be. It could be more, could be less. And I think the issue we're grappling with, especially in local government, is that people keep saying, look, it's not in the community. There's no community spread. And so that then comes to a lot of complacency, and you see it every day. We've recently cancelled a very beloved, well-known community event because, not in part, a little bit to COVID, in not being concerned about how to keep social distancing on the back of a lolly truck on Christmas morning. Mm-hmm. You know, so I'd just like to have a bit more comment about, I suppose, the community spread, and should we be complacent because it's not in the community?
Right, it's a good question. So at the moment, as far as we know, there is no community spread in Western Australia. I mean, we would be seeing it a lot more of it if there were. But what I was surprised by was when we were looking at our control group, right, because I came out as being not a control, right, which gave me a surprise. I mean, you know, when you find you're on the wrong side of the graph, it's quite worrying, right? And so I insisted that all of the controls were screened. 5 people showed up other than me who were had antibodies. So those are people, a couple of them that had no symptoms whatsoever, had no idea, although they'd sat next to people who had subsequently got it. And there were some people who just had a very minor cold for a couple of days and hadn't even given it a thought, right? So what I know from this is now a few months ago, right? So there must have been some level of community transmission to get that. And I suspect if we were to sero test everybody, we'd find quite a lot of hits. So there are people who've not actually even had any sign of the disease still could have been affected. So that's quite worrying, because it doesn't mean to say that the diabetes or the liver damage didn't occur. It's just they didn't have respiratory symptoms. Right? I had no respiratory symptoms. I had no sore throat. I had no cough when I had this. Okay. But this, back to the distancing thing, I have no idea whether 1.5 or 2 metres. It's a guess. Right? There's not, right? But when they did the science, it's 4 metres. Right? There you go. But that's not really workable in society. Right.
one more question up the back
Yeah,
there?
it might be a little bit odd, but on one of your screens there, you had on the clinical Phenomics page, one term that I was wondering if you could expand on was the direct injection Nanospray MS.
Yes.
What is that exactly?
Well, you were reading the detail, okay. Okay, direct injection nanospray mass spectrometry. So that's nano means small, directly means shove it straight in the mass spectrometer, right? And a mass spectrometer weighs molecules very accurately. And if you can weigh it accurately enough, you can say what the thing is, and also a bit about its fragmentation pattern. We do actually have a machine, through a transform mass spectrometer in the laboratory, which can do direct injection. That works on a microliter of sample, takes about 3 minutes, and it gives an incredibly good way of testing for the disease. That is the only machine of its type in Western Australia, and there's only 4 in the country, right? But these things where you have the minimum sample preparation, you can just shoot it straight into the machine, it's much, much faster. If you've got to separate all the molecules out chromatographically, you're talking about half an hour or so to do the analysis. And we want it in seconds or minutes.
I've got a really brief question and then we'll start to wrap it up. But the origins of the virus, with the bat and the pangolin being in a market within coughing or spitting or sneezing distance, is the world incredibly unlucky, or is this inevitable that a disease like this would
completely inevitable? I mean, the particular combination is peculiar and unique, but there are so many markets in the world, there are so many interactions between humans and animals which are, let's call them inappropriate or unusual or new. It's bound to happen. As human population density increases and we take up more and more space, we move into where animals live. We're closer to them, right? So these spillover events are bound to happen. And I think if you were to look over the last 30 years, you'd probably be able to list out at least 20 different zoonotic events. I mean, the original SARS is one, Ebola is another one, right? Where these things have been hidden away in animals in the jungle, and as people get close to them, they start to jump across. And as the human population increases and we encroach more and more on the land, it will get worse and worse. It's inevitable. It's part of population rise.
Inevitable.
Cheerful.
Cheerful. Yeah, good night, everyone. No, so before I hand over to the Vice-Chancellor again, I just want to thank you, Jeremy, for coming here tonight and for all the work that you do. It is staggering in times like this that there is a want of funding for the work that you do and the work that others do. Some of you may know I worked in the university sector for about 10 years. I used to be the research contracts lawyer at UWA for a while, and it was always a scramble back then, and that we're in the midst of this global disaster. It's amazing that there is not funding for this, and I continue to speak in Parliament about the need for funding for research and science of all sorts, and I'll continue to do so. And the community should call for this as well more often than we each do, because this is the kind of great work.
If I can just answer that, I mean, the scale of this is just unbelievable. So, Australia's been relatively, well treated by this disease, but what is the cost to this country? It's hundreds of billions of dollars, and yet we're talking about actually things in the millions of dollars that can make a difference, right? In the UK, Boris Johnson has just approved £500 million for mass spectrometric-based testing of the sort that we've been developing here. Actually, the stuff they're doing over there is not as good as ours, right? But I would say that, wouldn't I? Right? But that's the level. That's nearly $1 billion, right? And they're trying to roll that out over the next 3 to 6 months. That is a sign of desperation. When it gets out of control, that's the sort of money you have to spend, right? So spending a few million now save you billions potentially later on.
Absolutely, and that's science. So I'll hand over to Professor Eva Lennon now. Thank you.
Thank you very much, and it's my pleasure to do the vote of thanks. So first of all, Madeleine, thank you for organising this lecture series, and it's good to have Jeremy Nicholson kicking it off. And it was about a year ago that you and I were at an airport lounge. And not anymore. Those were the days when we flew around, and I was talking about the fact that Murdoch University has been in Rockingham since 1998, and we would like to start doing more things on our campus here. And we had this idea of a lecture series. COVID got on the way, but I'm so pleased that we have now started. This is the first of the lectures sponsored by yourself and Murdoch University, and I think the next one is in November, Professor Elaine Holmes. So thank you, Madeleine, and thank you for making this a reality. And then, of course, thank you, Jeremy. I did ask you not to scare people too much, do you remember? But, you know, it's better to know the facts and the science and the research than not, and I think you articulated particularly well that you personally have been lucky to have been able to utilize the science, because now you know more about yourself, you've been treated for your diabetes, and you have a good prognosis. But there are many people who don't have that same opportunity. And I'm sure you all know that, you know, we have had the pleasure tonight of hearing from a superstar in science. That's what Jeremy is. You know, he's one of the, well, probably the most well-known phenomic researcher in the world. And how lucky are we in Western Australia to have attracted Jeremy here and the team from Imperial and other people who have joined us. And as we said, COVID-19 is a global challenge, but here in Western Australia, we are leading research in that challenge through the AMPC and Murdoch University, but also other partners. And, you know, we are proud of that. And we've had some, you know, 2 years ago now, I think, we decided at Murdoch University to invest $30 million into the Australian National Phenome Centre. The federal government has given us $10 million. We have had some funding from the state government, but as Jeremy said, we need more. But also we've had charitable organisations supporting us and also some commercial operations. So this is a pandemic, a real pandemic that we need to invest in. And also, Madeleine, what you said, you know, the government needs to come to the party because, as Jeremy said, you know, investing $1 million, $10 million, what is it that we need? The economic outcome and the social and health benefits are immeasurable. And so we're very proud to be here. Thank you for, I also finally like to say thank you for those of you who are here. Thank you for taking part, but also those of you who are online. And, you know, it's a great pleasure to be a Vice-Chancellor University that is truly making a difference. So have a good evening, and I hope you sleep peacefully after Jeremy's. We actually had someone who came to visit the Australian National Phenome Centre and rang the following day and said, that was so scary, I couldn't sleep last night. Actually, the virus itself looks scary to me. It's like from some horror movie. But the fact that we have the Australian National Phenome Centre, the international network, and all of these researchers coming together to try to understand the virus, how it behaves, how it impacts on us, what are the short and long-term impacts of this virus, is what makes us sleep better at night. So thank you very much indeed. Have a good rest of the evening.
Thanks very much, Ava. And with that, we'll wind up. Just to remind everyone that the next lecture will be on the 5th of November. It will probably be similar to this, with less capacity in the room. Professor Elaine Holmes, Premier's Fellow and Director of Computational and Systems Medicine. Her lecture will be about of microbes, mice and men. So that'll be in the local paper and on Facebook sometime soon. And I'd just like to thank Murdoch again for letting us use this great space and helping us organise, and your great support. And also thank my team at the electorate office who have done a wonderful job during the whole COVID crisis, helping the community, but also bringing this together tonight. And thanks particularly to Kate Gerbiel who brought this together. Have a nice night, everyone. Rest assured, science is onto it. It's a long journey ahead, but if we support our scientists and our researchers, there is light at the end of the COVID tunnel. So thanks very much again, and safe travels.